So today we're going to start talking about two different types of random variables that we can encounter. So up until this point, we've talked about just our generic discrete random variables, talked about how to calculate the mean or expected value, how to calculate and interpret standard deviation. And so what we're going to talk about with these binomial and these geometric random variables. So we're going to talk about binomial today, geometric tomorrow. We'll do kind of a combo of the two on Monday. But what we're looking at is when we think back to the first half of our unit. In the first half, we talked about basic probability calculations. So we talked about the general addition rule when we wanted one event or another. We talked about the general multiplication rule when we were looking at a sequence of events. Okay? And so we had all these different techniques, different formulas we could use to calculate different probabilities. Now, those multiplication rules, those addition rules can sometimes become a little bit complex or a bit time-consuming when working with those. So what happens here is if those random phenomena that we're studying and we're looking at a sequence of events happening over and over again. So we're going to perform a random phenomenon multiple times. If it follows a binomial or a geometric setting, then what we can do is we can alleviate some of the complexity involved in making some of those calculations, some of those probability values. And so what we're looking at with these binomial and geometric models, we're seeing the same chance process, the same random phenomenon being repeated several times. And we're usually interested in whether a particular outcome does or doesn't happen. So there's going to be certain conditions that must be met to tell us that we're working with a binomial setting or working with a geometric setting. But when we have that in place, we can use the binomial model, we can use the geometric model to calculate things a little bit more quickly, a little more efficiently. And so a couple examples there to test whether someone has ESP. You choose one of four cards at random. Ask the person to identify the card without seeing it. Do this 50 times and see how many cards the person identifies correctly. So this would be an example of a binomial setting. And we'll talk about what makes it binomial here in a second. In the second example, the game Pass the Pigs, the player rolls a pair of pig-shaped dice. On each roll, the player earns points according to how the pigs land. If the pigs land on opposite sides, which they call a pig out, the player loses all their points. So how many rolls on average will a player get before pigging out? And so this is going to be a geometric setting. And so what's going to happen is when we get these types of scenarios, we're going to check for conditions to determine if we have what we need to use a binomial distribution or if we have what we need to get a geometric distribution to maybe simplify some of the processes that would be involved with that particular scenario. So for the binomial setting, so this is the one we're going to focus on today, and then we'll talk about geometric tomorrow. But for the binomial setting, when I define a binomial random variable, we are counting the number of times the outcome of interest occurs in a fixed number of repetitions. And so in that definition at the top there, I've highlighted the two key pieces. For a binomial random variable, we're looking at the number of what we call successes, and we have a fixed number of trials. We are going to perform the random phenomenon this many times no matter what, and we're going to look at how many successes occurred within those amount of trials. Now, as far as identifying a binomial setting, so the first couple problems in your homework today are going to give you a description like we saw on the last slide, and they're going to ask you whether or not you have a binomial setting. So the first thing you're looking for, these four conditions that you're testing, is first, are there only two outcomes that we're interested in? We typically label them as a success or a fail. Now, don't think of it like in real terms of like a success means something good happened, okay? This isn't in context of the problem that we call success fail. We're just saying there's a certain outcome we are looking for. That's our success. There's another outcome we don't want to have happen. That's our fail. So when I'm looking at the scenario as a whole, am I only looking at two outcomes? Either I succeed and get what I was looking for or I don't. The second one is that the trials must be independent of one another. And we've talked about this a couple different times throughout this unit already. So as I go from one trial to the next, those trials must be independent. The one should not affect the next, should not affect the next, and so on. So we need to be able to justify independence between trials. And then if you notice on the third one, I have it circled and starred. This condition is what separates a binomial setting from a geometric setting. So when we talk about geometric random variables tomorrow, our conditions are going to look almost identical. The only difference will be this third condition. The binomial and the geometric setting have different things that we look for. So in that third condition, we're saying we have a fixed number of trials. So they have to tell us ahead of time, we are going to do it this many times and that's it. And we talk about the number of trials as a lowercase n. That's the notation we're going to utilize, so make sure you get that down as well. So when you see that lowercase n, they're telling you that's the number of trials for that particular random phenomenon. And then the fourth condition, the probability of success, which we're going to denote with a lowercase p. So that's another notation that you want to make sure you get down. But the probability of success must be the same for each trial. Now that second condition and that fourth condition kind of go hand in hand. The trials being independent means that from one trial to the next, my probability of success is going to remain the same. Now there are instances where we will run into problems with this independence condition. When we sample from a finite population, if I'm sampling without replacement, I violate this independence condition. And so we're going to talk about a fix or a way around this particular condition when it fails in certain instances. But for the most part, we're looking to make sure we can justify that independence. So, when we look at the description for a scenario, we have three different scenarios here. If we start with the one on the left side, genetics say that children receive genes from each of their parents independently. Each child of a particular set of parents has the probability, 0.25, of having type O blood. Suppose these parents have 5 children, and we let our random variable x be the number of children with type O blood. So if I want to know if that is a binomial setting, can I use this binomial distribution to make my different calculations? We start by just going through the list of conditions. So when you're doing this, when you're justifying a binomial setting, you need to comment on all 4 conditions, or you need to point out the one that fails. So as we look at this first setting, do we only have 2 outcomes we're interested in? Okay, what would be a success in this case? Having type O blood. What would be a fail? Not having type O blood. So one thing that's sometimes a little tricky, you got to think about how we're looking at this, because there are more than 2 types of blood. There's A, B, B, and O. So technically, in a scenario like this, in general, we would have more than 2 outcomes. But in this particular instance, even though there's 4 different blood types, we're only interested in one. So either we get type O blood or we don't. That's what allows us to use those 2 outcomes. Okay, so we think of it in terms of the success and the fail. So then we check independence. From one child to the next, would they be independent of each other? Yeah, and we know that in this particular instance because what? It actually says it, right? Now that's not always going to be the case, but they actually tell us that the trials are independent in the problem. So sometimes we might have to justify it by assuming independence. Other times they might actually tell us that that's what's happening. But so we have our independence. The next one, do we have a fixed number of trials? Yeah, the 5 children. So n would equal 5. We're setting it at they're having 5 children. So that's our fixed number of trials. So we go to our last condition. Is the probability of success, the probability of type O blood, going to stay the same for each child? Right, there's a 25% chance for each child, so the probability of success is going to stay the same every time. So all 4 conditions are met. So on the homework, or on a quiz or a test, you would have to make sure you comment on all 4. How is each one of these conditions met? This tells us we have a binomial setting. And then we can define the binomial distribution using that n and that p and the other things we're going to talk about here in a little bit. In the second example, the one in yellow there, we shuffle up a deck of cards, turn over the first 10 cards one at a time, let y equal the number of aces you observe. So as we examine this setting and try to establish whether or not it's a binomial setting, are there only 2 outcomes we're interested in? Yeah, either we get an ace or we don't. So a success would be an ace, a fail would be anything else. Do I have independence? So as I go from one card to the next, are the draws independent of one another? No, why not? Because we're not replacing the card. So when I take a card and I draw it, I flip it up, I leave it out, I go grab another card. We talked about this back in that first half of the unit with those probabilities. Every time I remove a card from the deck, what happens to the next probability? It changes, right? Because I've changed my sample space. Once I remove a card, I'm not drawing from 52 cards anymore, I'm drawing from 51, then 50, then 49, and so on. So I fail the independence condition. So this cannot be a binomial setting because that independence is important to that distribution. So that would be what we comment on. We don't have independence, this is not a binomial setting. In the last example, we shuffle a deck of cards, turn over the top card, put it back in the deck and shuffle again. Repeat this process until you get an ace. Let the random variable W be the number of cards required. So now as we start going through our list, do we have 2 outcomes? So do I have a success? What would the success be? An ace. My fail would be anything else. So 2 outcomes. Would I have independence this time? This time I will, because what are we doing this time? We're replacing the card every time. So every time I put it back in there, I'm keeping my probability of success the same. So I have independence and the probability stays the same. Do I have a fixed number of trials? No. And when we look at how they define the random variable, we can actually see that. It says let the number of cards required before we find that first ace. So we have no idea how many trials that's going to take. We haven't fixed it ahead of time. So this would not be a binomial setting. So on those first couple homework problems, that's what you're going to be looking at. Based on this scenario, do I meet the 4 conditions? If I do, then it is a binomial variable and I define it. If it's not, I have to comment on which condition fails. Okay? So then when we run into our binomial settings, so once I've confirmed that we have a binomial setting in play, the next thing I can start to do is work with the binomial model to calculate any of the values I would need associated with this scenario. So take a minute here, copy down these formulas. As you're copying them in your notes, maybe leave a little bit of space to add some things here. So as you're copying these down, note, whenever we define a binomial setting, we need to make sure we define our random variable. So in this case, we're just using the generic letter x. X would be the number of successes in a fixed number of trials. And then the other two pieces we always need to define is what are the fixed number of trials n, and what is that probability of success p. So all three of those pieces need to be defined every time before we start working with any of the calculations. So most of the time, when we're working with these binomial distributions, we're worried about probability. That's what this whole unit's been about. So we're working with probabilities of different events. And so when we look at that formula, now the formula looks a lot more complicated than what it really is. So when I'm looking at this formula, the first thing, the notation. So when I'm using this formula, I'm calculating the probability of an exact number of successes. So my capital variable x is the number of successes in n trials. The lowercase x is the actual value I'm looking for. So I'm going to run 10 trials. I want to know the probability of getting exactly 7 successes. So when I write my notation, and this is again, just like with the probabilities in the first half of the unit, you have to write the notation. If I was modeling that, I would say the probability that x is equal to 7. I want exactly 7 successes. Now when we look at the formula here, the first part of the formula, this notation right here, what this tells us is the number of ways to get this many successes. We read this notation as n choose x. Number of trials, choose the number of successes we want. So this is calculating the number of ways to get this many successes. The other thing you want to make a note of here, this is the notation. So these formulas, the other good thing about these, you do not have to have these memorized. They'll be given to you. You just need to know how and when to use them. But when I'm looking at this formula, this is how it's going to be presented to you. In the calculator, though, because we're going to talk about how to do these things in the calculator, the notation is going to look like this. It's going to say NCX, or in the calculator's position, it's going to be NCR. So there's two different notations for the same process. This is the one that they get on the formula sheet, so that's the way I presented it here. But this is what it's going to look like in the calculator. And again, we'll talk about how to plug that in when we get to that point. Now the rest of this, again, if we think about this in terms of what these things mean, remembering this formula actually becomes fairly simple. So it looks really complicated, it looks really drawn out. But if I look at that first part, knowing that that's the number of ways to get that many successes, and I know it's a button I can use in the calculator, the rest of the formula is taking the probability of success raised to the number of successes. So I'm just taking the probability that I succeed, raise it to the number of times I want to succeed. And then if P is the probability of success, what is 1 minus P? Which would be a complement, but what would we call it? If it's not a success, it's a fail. So that 1 minus P, that's just the probability that I failed. So they're complements of each other. One is the probability that we succeed, the other is the probability that we fail. And then again, if we think about this, not in terms of all the letters, but what they represent, this n minus x is the number of fails that I want. So that NCX is a button we have in the calculator. When I go to set up the rest of the formula, it's the probability of success raised to how many successes I want times the probability that I fail raised to the number of fails that I want. Now, what's nice about this formula here is when we have the binomial setting, like I said, it simplifies a lot of those earlier processes we talked about in the first half of the unit. So think back to yesterday in our activity. Yesterday in the activity when we calculated the probability, so the theoretical probability that we win $1 in that dice game. Okay, the way we set it up was we used our general multiplication rule. We said the 3 dice are like a sequence of events. $1 meant that I rolled a single 1. So when I thought through that process, I had a 1 out of 6 chance of getting a 1. Then I had a 5 out of 6 chance of getting something else, and another 5 out of 6 chance of getting something else. So we said once I get the 1, the next 2 dice have to be something different. But then we said, okay, well, if I calculate this, this is just the the value for the first die being a 1. So then we had to realize that on top of that, we had 3 different possibilities for this particular scenario. I could get the 1 on the first roll, the second roll, or the third roll. And so we had to take this probability and multiply it by 3. So if I'm thinking through that process, right, it takes a little bit of time. Now, if I were to do this with multiple, like more dice, like 10 dice, 20 dice, things like that, this becomes a lot more drawn out. And so that's where this binomial model comes into play. If I think about what we were dealing with. Yesterday, there were 2 outcomes. I got a 1 or I didn't. The rolls were independent of one another, rolling the dice, independent on each trial. I had a fixed number of trials. We rolled the dice 3 times. And each probability of success was the same every time. So if I look at what this formula is asking for, this NCX is the number of ways I can get the successes that I want, the number of ways I get one success. So if I was using this binomial formula, the first part of my calculation would be 3 trials, choosing 1 success. My success was rolling a 1, so the probability of success was 1 out of 6. I wanted 1 single success, so I would take that 1/6 raised to the first power. My probability of fail would be 5 out of 6, and I needed to fail twice. And so what you notice is the process we used and the process we're talking about today are exactly the same. 1 fail, 2 successes, 1 success, 2 fails, and then 3 different ways that can happen. But using this model, I don't have to worry about the number of ways it can happen because this can get really complex really quickly. If I was rolling 4 dice and I wanted 2 1s, that could be on the first and second, first and third, first and fourth, second and third, second and fourth, third and fourth. I get a lot of different combinations. So instead of having to keep track of that myself, this formula will keep track of it for me. 4 successes, choose 2, it calculates that value. Then all I need to do is, what's my probability of success and how many successes do I want? What's my probability of failing and how many fails do I want? And then I just put it all together in the calculator. So that's what that's going to look like, and we're going to go through a couple examples here. Now, keep in mind, this formula works when we want an exact number of successes. So I'm running 10 trials. I want exactly 6 successes. If I start to look at multiple successes, then I got to attack the problem a little bit differently. And again, we'll talk about that as we go. The other part here that we want to be aware of is when I'm working with a binomial distribution, anytime we're working with these random variables, we're always interested in the expected value. So when I'm working in this binomial setting, what do we expect to happen in the long run? What does the law of large numbers say about what I can think, or what I should be expecting if I did this multiple times? So this is just calculating the mean of our distribution. This is like calculating the mean for our random variables. So we had a very specific formula for just your general discrete random variables. We took each value times the probability, added it to the next value times that probability, and so on, and we just continue to add them up over and over. With a binomial distribution, if I want to know the expected number of successes, all I have to do is take the number of trials times the probability of success. If I want the standard deviation associated with that, okay, my formula is the square root of the number of trials times the probability of success times the probability of fail. So rather than that long, drawn out, each value times the probability plus the next value times the probability and so on, or the standard deviation was even more drawn out, I have these simple formulas I can use. So in that binomial setting, if I want the expected number of successes, n times p. Standard deviation, n times p times the complement, and then the square root. So the way we use this, and we're going to talk about how to calculate these things by hand. There's also going to be a process in the calculator we can do. But if we go back to our genetics scenario from earlier, so we said each child has a 0.25 probability of having type O blood. This family is going to have 5 kids. We already established this was a binomial setting. So it says how many of the children can the parents expect to have type O blood? So they're asking what's the mean of this distribution. So if we looked at our numerous families under these same conditions, on average, how many children would we expect to have type O blood? So the first thing, before I can start any calculations, I need to define my random variable. Or I'm going to reword that. Okay, so my random variable, I'm just going to use the letter x. I could use any letter though. We're looking at the number of kids with type O blood out of 5 kids. We already established earlier that x is binomial. With our fixed number of trials being 5 and our probability of success being 0.25. So I have to define these things before I can start working with that binomial model, those different calculations. Sometimes they'll define the variable for you in the problem, so you're taking care of that already, but then you might have to justify that it's binomial. And if it is binomial, what's the number of trials? What's the probability of success? You have to define those things first. And so now when I go to actually answer the question, I said, how many children can the parents expect to have with type O blood? So if I want to calculate my mean, the formula said take n times p. So 5 children, 0.25 probability. And so what should they expect? $1.25. Now, when we calculate these means, understand that we're talking about this specific family, but when we calculate this expected value, we're not saying that this particular family should expect 1.25 kids with type O blood. I can't have a kid with type O and then another kid with a quarter type O blood. So what we're calculating here is on average. If we looked at numerous families with this same setting, on average, these types of families should have 1.25 kids with type O blood. So over numerous trials, this is what we expect to see on average. And then for standard deviation, so that's our formula, square root, n times the probability of success times the probability of fail. So if we throw that in the calculator real quick, what do we get for a standard deviation? .97. Okay. So then when we interpret, if we looked at numerous families under these settings, any particular family we select will typically differ in the number of kids with type O blood from the true mean by about 0.97 kids. So on average, any individual family we select will differ from the mean by about 0.97. So just like it was before, just a different way of calculating it. Okay? So that's what that would look like when they ask you for that expected value, that mean, and that standard deviation. If we start talking about the probabilities, though, this was the more complicated formula. So same setting. This time, though, we want to know what the probability that exactly 3 of the children have type O blood. So first thing we would normally do is we would define our random variable, but we've already done that. We're using the same problem. We would establish that it's binomial. N is 5, P is 0.25. And then when we actually go to calculate here, the notation, if X is the number of children with type O blood, what they're asking us to calculate in notation is what? The probability that X equals 3. So you have to define the probability you're calculating with the notation. So we're looking for the probability that X is 3. We want exactly 3 kids with type O blood. So from the previous problem, we knew the number of trials was 5. We knew the probability of success is 0.25. When I go to plug into my formula, the first part, number of trials, choose the number of successes. Next part, probability of success is 25%. I want 3 successes. Next part, probability that I fail. And how many fails do we want? 2. So I've got 5 total trials. If 3 are going to be successes, 2 need to be fails. And so if we fill it in that way every time, like I said, the formula becomes a lot less complicated to remember. Now, as far as plugging this in the calculator, so go ahead and get your calculators. So when we go to do this in the calculator, the first part was that 5 choose 3. So when you type that in the calculator, you start by entering 5. So put the first number in. So we go to 5, and then we're going to have to choose the combination function. So we go to math. We go over to PROB. And we said that that notation could also be that NCX. So in this case, NCR is the way they label it in the calculator. So I select option 3. And so now it's formatted my numbering a little bit differently here. So now I've got the 5 choose. I want 3 successes. And then it keeps you in the subscript portion of the formula right now. So if you hit the right key, it gets you back to your normal setting. So I've got 5 choose 3. That's the first part of my formula. Then I'm just copying the rest exactly like I see it. Probability of success was 0.25. Raised to the third. Probability of fail, 0.75. Raised to the second. And so on the homework, obviously you would write out, if you're using the formula, you would write out what this looks like. And then once we get it all entered, we hit enter, and we get our probability. So for a family with 5 kids in this particular scenario, there's about an 8.8% chance that exactly 3 kids would have type O blood. So when we plug that in the formula, we get that 0.088. Now, as far as the exact number of successes goes, the formula itself really isn't that bad, really time-consuming to plug in. So it would be a perfectly acceptable option for a situation like that to use the formula. If you do the formula, you need to write it out. Okay? There is a function on the calculator, though, that will allow us to do the same thing. So if you go into your calculators again, we're going to go into our distribution menu. So back when we did like normal CDF, inverse norm, things like that, it's been a while. The distribution menu we find by taking or hitting second, and then the vars key right below the arrows. So second, vars. And then the function we want, the quickest way to it is just by going up. And about top third there, we see a binom PDF and a binom CDF. So when I scroll up to those 2 functions, these are going to be my binomial distribution calculations. So something you might want to write down here, binom PDF. When I select binom PDF, I'm looking for an exact number of successes. So like the scenario we're working on right now, we want exactly 3 kids with type O blood. That is a binom PDF problem. In a second here, we're going to go through an example where we calculate the probability that they have less than 3 kids. When I want less than or greater than a certain number of successes, so I'm looking at a range of successes, that's when we're going to use binom CDF. So PDF for an exact number of successes, CDF for multiple numbers of successes. So for our problem, probability that x equals 3 exactly, we're going to select that binom PDF option. So go ahead and select that. It's going to ask for exactly what it wants. So the number of trials we're performing is 5. The probability of success was the 0.25. And then the x value is the number of successes we want. So in this case was 3. So then we hit paste on the homework or on a quiz or a test. If this was the option that you used to calculate the probability, you would need to copy this onto your sheet of paper. So once you have it pasted in the calculator, you need to copy this down. I need to see which function you chose, PDF versus CDF or binom versus geomet. What did you plug in for the different parameters? And then when we hit enter here, we get the same value we got earlier. So when we're doing this type of problem, either the formula like we did the first time, or you need to write out what you're plugging in the calculator for that binom PDF in this instance. So 5 trials, 25% chance of success, 3 successes total. So I need to see one or the other in terms of work, however you want to attack that. Again, when it's an exact number of successes, the formula itself is not that bad. So you can use it, or you can use the Binomial PDF if you want to use that. But now when I switch this up a little bit here, so now if I change it to what's the probability that fewer than 3 of the children have type O blood. So when I look at that as a problem here, in notation, what would that look like? X is less than 3. So this time we're not concerned with one single number of successes. I want the probability that my random variable takes on any value less than 3. So if I were to attack this with the formula, what would I have to consider here? If I want X less than 3, then which outcome specifically do I need to account for? How many kids could have type O blood? 2, 1, or 0. There's 3 different outcomes. If I was going to use the formula, I'd have to use the formula once for 2 children. 5 choose 2, 0.25 to the second, 0.75 to the third. Then I'd have to do it for 1, then I'd have to do it for 0. And then what would I do with those 3 probabilities? Add them together. I want one or the other or the other. So attacking this with the formula is probably not your best option. It's going to be a lot more time consuming, a lot more setup. Okay? So when we're looking for a range of successes like this, we're going to use that other function in the calculator, which was that Binomial CDF. So when you go into your Binomial CDF, so second vars, scroll up to Binomial CDF. When we go to plug in our values, and these are the ones that are a little bit trickier. The first part's pretty straightforward. That's never going to change. My fixed number of trials is still 5. My probability of success is still 0.25. But my X value, I got to be really careful with here. What this calculator is going to calculate with the Binomial CDF, it's going to calculate all of the probabilities up to wherever you tell it to stop, and it's going to add those up for you. So rather than you having to calculate each individual probability and then add them together yourself, the calculator is going to do it all for you, but you have to tell it where to stop. So if I want the probability that X is less than 3, where do I want the calculator to actually stop here? It's going to start at 0 and work its way up. Where do I want it to start? Or I'm sorry, where do I want it to stop at? At 2. 2 is the last viable option for us. Okay? So even though I'm doing probability that X is less than 3, the number I actually plug in for my X value is 2. So what this calculator is going to do is it's going to calculate the probability of 0, of 1, of 2, and then it's going to add them all together. So on your sheet, you would copy down. Once we paste, I've got Binomial CDF, 5 trials, 25% chance, and I'm stopping at 2. And then I hit enter, and I get my probability. So we got about an 89.6% chance. So when you're working with that Binomial CDF function, it's going to be really important that you pay close attention to where you're cutting yourself off at. This particular calculation would be identical to this calculation. So they're going to sometimes have less than, sometimes less than or equal to, sometimes greater than or equal to. Every time I change it, it changes what I'm doing in the problem. So when I did binomial CDF originally, x was compared to 3, but I plugged the number 2 in. So I wanted to stay strictly less than 3. But if they wrote it as x less than or equal to 2, I want 2 or fewer children, then I actually do plug the value given into my binomial CDF function. So sometimes that x value will match what's in the notation, sometimes it won't. You've got to be really careful with it. When we switch to greater than, so should a parent be surprised, or should the parents be surprised if more than 3 of the children have type O blood? So now we're saying, what's the probability that x is greater than 3? Now in this case, when we use the calculator, when we use that binomial CDF function, just like our table A only could calculate things to the left, my binomial CDF can only calculate probabilities less than. It's always going to start at 0 and work its way up until you tell it to stop. So if I'm going to attack a greater than problem, just like we did with our normal distributions in table A, we're going to use the complement rule to attack this. So we're going to take 1 minus binomial CDF. The first part is pretty straightforward. 5 trials, 0.25. But then when I get to that last part, I got to really think about what I want to put in here. So if I think about what's going on, I want to get rid of everything I don't want. The calculator is going to go from 0 up to where I tell it to stop. So if I'm looking at probability that x is greater than 3, what values do I actually want? How many kids do I want to have type O blood? 4 or 5. So again, if I wanted the formula, I could do the probability of 4, do the probability of 5, and then add the results. But again, it might take a little bit longer. So what I need to do is I need the calculator to calculate everything I don't want. If I want 4 or 5, I want the calculator to calculate all the way up to what value? 3. So I'm going to go all the way up to 3, so this time the number does match. And when you plug that in the calculator, you plug it in exactly like you see it. Plug in the 1 minus, hit your second vars, go to binomial CDF, plug in the appropriate values, and then it'll calculate whatever that percentage comes out to be. If that percentage is extremely low, then yes, the parent should be surprised. If it's not very low, then no, they shouldn't. But that's how you would attack this particular type of problem. Last thing real quick here. When we sample from a finite population without replacement, we talked about this earlier, we run into a problem with our independence. So a fix for this, because a lot of real-world scenarios require the use of sampling from a finite population without replacement, we are still able to assume independence as long as the sample we take, the number of trials we use, is less than 10% of the entire population. So if the sample that I select is less than 10% of the entire population of interest, my probabilities aren't going to change enough to make a big difference, and so we're okay to proceed as if independence was actually met. Okay? And so then you have these following problems here, which is posted on Google Classroom.